Hello everyone, I'm Ashkan Safari, an MSc student of Computer Science from Institute for Advanced Studies in Basic Sciences, Zanjan, Iran, and I'm going to present our paper entitled Path Planning in a Weighted Planar Subdivision under the Manhattan Metric. This paper is a joint work in cooperation with Dr. Mansoor Davoodi and Mr. Hosein Enamzadeh. This talk is especially relevant to those who are working and interested in optimization and path planning problems. By the end of this talk, I hope you will be familiar with our algorithm. I have divided my presentation into four main parts. First of all, I'm going to give a short introduction on path planning and weighted region problem. After that, I'm going to state the problem. This brings me to the next part, which is our contribution. In this part, the proposed algorithm and the basic idea for proving the correctness of the algorithm will be explained. Then I'm going to talk about the generalization of the proposed algorithm to the three-dimensional case. Finally, we will have a brief conclusion and future research for further improvements. Path planning problem is one of the fundamental problems in computer science and robotics, which is a practical problem in computational geometry, computer games, computer animation, and industries. In the classical version of path planning, the workspace contains some obstacles, and a path between two start and destination points must avoid these obstacles. However, in a general formulation of path planning problem, called weighted region problem or WRP for short, each obstacle has an associated weight, and the path is allowed to enter them at extra costs. In fact, these weights represent the cost per unit distance of movement in the obstacles, or we can say weighted regions. This problem was first introduced by Michel and Papadimitriou in 1985. An important theoretical result on WRP in 2012 has shown that this problem cannot be solved in the algebraic computational model over the rational numbers under the Euclidean metric, which justifies the search for approximate solutions as opposed to exact ones. Also, there are several variants and special cases of WRP due to the metric and the shape of weighted regions. For example, in one of the papers, the authors have solved the problem in the presence of isothetic obstacles. Precisely, the boundary edges of obstacles are either vertical or horizontal line segments. For this case, they have presented two polynomial time and space algorithms. Now let me state the problem. We have a subdivision of the plane into polygonal regions with n vertices. Each region has an associated positive weight. The weight of an edge, or let's say boundary of regions, in the subdivision is the minimum of the weights of the regions that are incident to that edge. The goal is to find a minimum cost path between S and T where the distances are measured under the Manhattan metric. Since a simple polygon with n vertices can be triangulated in O of n like n time and O of n space, and our proposed algorithm is able to find an optimal path in O of n squared time and space, without loss of generality, we assume all the regions to be triangular regions. Now let's move on to the next slide and see a general overview of the proposed algorithm for solving this problem. Our method for solving this problem is reducing the problem to a graph searching problem. As a matter of fact, we have proposed an algorithm for constructing a graph which contains the minimum cost path between S and T under the Manhattan metric. The graph is called G. Let's take a look at the graph construction algorithm. We consider horizontal and vertical lines passing through vertices of the subdivision, which are S, T, and vertices of the triangles. The set of vertices of the graph are S, T, vertices of the triangles, and the intersection points among considered horizontal and vertical lines. We also add the intersection points among horizontal or vertical lines and the edges of the triangles to the set of vertices of G. Also, the set of edges of G are the line segments between consecutive vertices. To be precise, the edges of G lie on the considered horizontal lines, vertical lines, or the edges of the triangles. For example, here you can see the graph on this workspace. Note that here, for simplicity, we haven't triangulated the white region with weight 1. Precisely, we can apply the proposed algorithm in a polygonal subdivision in which the regions are not triangular. The triangulation of the regions just helps us for showing that G contains the minimum cost path between S and T. The graph has O of n squared vertices and edges and is constructed in O of n squared time. In fact, for constructing the graph, we can use one of the line segments intersections algorithms, which computes all k intersections among n line segments in the plane in O of n like n plus k time. Since G is a planar graph, the minimum cost path between S and T is obtained in O of n squared time. Since our metric for measuring the distance is Manhattan, we can convert any path between S and T to a path which consists of vertical and horizontal line segments without increment in the cost of the path. But in G, some edges, which are located on the edges of triangles, are oblique. These edges are useful when two triangular regions are close to each other and the region among them has lower weight than these triangles. For instance, consider in this workspace W1 is much less than W2 and W3, and we want to go from P to Q. If a path between these 2 points be completely horizontal and vertical, it will enter one of these 2 triangles, and the cost of path among blue line segments is much than the red one. Therefore, the path along the red line segment has lower cost than the blue ones. Note that the weight of an edge in the subdivision is the minimum of the weights of the regions that are incident to that edge. So the weight of this edge and also this edge is equal to W1. Now I'm going to talk about the basic idea behind the proposed algorithm that the correctness of the algorithm is based on it. According to the graph construction algorithm, horizontal and vertical lines are considered passing through vertices of the subdivision. We call the part of the workspace which is surrounded by 2 consecutive horizontal lines a horizontal lane denoted by LH. A vertical lane denoted by LV is defined similarly. In this figure, this part which is surrounded by these horizontal lines is an LH. The basic idea behind the proposed algorithm is this. Consider 3 paths pi1, pi2, and pi3. All of these paths have the same start and destination points, here S prime and T prime, and are passing through k triangular regions. We have shown that if the weighted length of pi2 is less than pi1, then the weighted length of pi3 is also less than pi2. Therefore, for a path pi which enters an LH in a point S prime, suppose S prime is located on one of these 2 lines and passes through k triangular regions and finally exits the LH in a point T prime, there exists a path like pi prime, which the horizontal subpaths in pi prime are located on these 2 lines, and the length of pi prime is not more than pi. This idea brings us to this lemma. In fact, we have proven that for 3 consecutive paths, pi1, pi2, and pi3, by consecutive I mean that they have the same starting and destination points. So for 3 consecutive paths, pi1, pi2, and pi3, which are located inside an LH or LV, if the weighted length of pi2 is less than pi1, then the weighted length of pi3 is also less than pi2. The proof of this lemma is based on the triangle similarity theorems. For instance, look at this figure where pi1, pi2, and pi3 are passing through these two triangular regions. According to the triangle similarity theorems, x1 over h is equal to z1 over h prime, and z2 over h is equal to x2 over h prime. So we have the following equation, which shows h over h prime is equal to x1 over z1 is equal to z2 over x2. Since h over h prime is constant, the proof can be generalized for any k greater than 0 triangles between s prime and t prime. As a matter of fact, the proof of this lemma is much more complicated than these three equations, but I just wanted to give you the basic idea for proving this lemma. Finally, for the planar case of this problem, we have shown that for a shortest path pi1 under the weighted Manhattan metric in the continuous workspace from S to T, there exists a path pi2 from S to T on the constructed graph such that the weighted length of pi2 is not greater than pi1. Therefore, the weighted region problem in a planar polygonal subdivision with positive weights under the Manhattan metric can be solved in O of n squared time and space, where n is the total number of vertices of the subdivision. Now let's move on to the three-dimensional case. It has been shown that the problem of finding a shortest path under any LP metric in a three-dimensional polyhedral environment is NP hard. Therefore, here we have considered a specific variation where the regions are rectilinear, and we have generalized our algorithm for this case. For constructing a graph in this case, we consider planes orthogonal to the x, y, and z axis, passing through S, T, and vertices of the regions. By intersecting these planes, the set of vertices and edges of the graph are obtained. The constructed graph has O of n cubed vertices and edges. Therefore, by using Dijkstra's algorithm, the minimum cost path under the Manhattan metric is obtained in O of n cubed like n time. Since a metric for measuring the distance is Manhattan, it is easy to show that an equivalent path between S and T exists where all the subpaths between consecutive breakpoints are located on the considered planes. Finally, by using arguments similar to the planar case, we can show that the graph contains a minimum cost path between S and T. Therefore, the weighted region problem in a three-dimensional workspace among rectilinear regions with positive weights under the Manhattan metric can be solved in O of n cubed like n time and O of n cubed space, where n is the total number of vertices of the subdivision. Now let me briefly summarize what I've said so far. Here we have studied the problem of finding the shortest path among polygonal regions with positive weights, where distances are measured under the Manhattan metric. We propose an O of n squared time and space algorithm for solving this problem. By using the triangular inequality, it is easy to see that the length of a path under the Manhattan metric is at most the square root of 2 times of the length of the path under the Euclidean metric. Therefore, the proposed algorithm is also a square root of 2 approximation algorithm for solving WRP under the Euclidean metric. We also generalize our algorithm for the case of rectilinear regions in 3 dimensions and propose an O of n cubed like n time and O of n cubed space algorithm for this case. For the future work, improving the time complexity of the algorithm and providing a better approximation factor for the Euclidean metric remain open. However, for improving the time complexity, we have proposed another algorithm for the planar case, which is able to compute shortest path in O of n log squared n time. Thank you for your attention.